Hey everyone, welcome to my talk on quantum cybersecurity. Let's get started. So, here's a quick agenda of what we're going to be covering in this presentation. First of all, we're going to be covering some classical encryption methods. These include RSA, ECC, Diffie-Hellman or DH, and so on. Then, we're going to have a look at Shor's algorithm. Shor's algorithm is promising to break these classical encryption methods that you and I commonly use on the internet today. We'll see what it's about and how it works. Finally, we're going to be reviewing some quantum-resistant classical encryption methods that are resistant to quantum attacks like Shor's algorithm. So, to start off with, what is digital security? When you talk about securing our data on the internet, what exactly does that refer to? Well, digital security is a pretty broad term, and it's essentially defined by the process of protecting devices, your data across the internet, and even at rest, let's say on your computers or otherwise, from misuse. So in this case, for this presentation, we won't be covering all of the different aspects of digital security. Rather, we'll be focusing on cryptography, because that's where Shor's algorithm promises to cause a lot of mayhem in classical cryptography. So here's a quick example of what encryption is. Encryption is the process of taking data that you already have and converting it to gibberish using mathematical formulas. So as an example, confidentiality. So let's talk about encryption. Encryption is the process of taking your data and encoding it using a mathematical algorithm. This encoding will ensure that anybody who gets access to your data won't be able to understand, read it, or really make any use out of it. And this promotes confidentiality of your data, so you can rest at ease knowing that nobody will be able to read or understand what your data is. So here's an example of encryption at play. This is Dave. Dave has some data that he wants to encrypt. So what is he going to do? Well, first of all, he's going to take this document and encrypt it into some gibberish using a mathematical formula. Now, once he converts it to this gibberish, he's going to send this gibberish off to his friend, Alice. Now, Alice, not being able to read any of the data, she is the intended recipient, so she technically should be able to read it, but she can't because it's gibberish. So what she's going to do is she's going to use her key, which is essentially able to reverse the encryption process and get the original data that Dave sent. Hence, this sort of loops back into an entire chain where you can send encrypted data and then the receiver can decrypt it using the key that he or she has. And so this is essentially one kind of encryption, but it's a very popular one. And this is basically what you see on the internet and many other data communication methods. This is essentially the process that's being done. So here are some examples of encryption methods on the internet. Some of them include RSA, or the Rivest, Shamir, and Edelman algorithm. These are the names of the creators who created this algorithm. There's also, so some examples of these algorithms include RSA, or the Rivest, Shamir, and Edelman algorithm, named after the creators of this algorithm. Some use cases for this algorithm include web browsers, emails, VPNs, and so on. We also have another algorithm called the Diffie-Hellman algorithm, or DF. This algorithm is commonly used in internet protocols like TLS, SSH, IPsec, and so on. Finally, we have ECC, or elliptic curve cryptography. You'll know about this if you research. You'll know about ECC if you research into Bitcoin, cryptocurrency, hashing, and that kind of stuff, because it's very commonly used in that industry. So here's an example of classical factor finding. So in this example, we want to find the factors of the number 15. Well, that sounds pretty easy. It's just 3 and 5, right? 3 times 5 is 15. There we go. But remember that we as humans can do this quite easily, and it's pretty obvious what the answer is. But for a computer, while there may be more optimized methods, let's just go with the generic brute force example. So a computer, to be able to find the factors of the number 15, it's going to have to go through all of the possibilities of factors that can multiply together to create the number 15. So once this algorithm brute forces all of the possibilities, and again, there may be more efficient algorithms, but for our specific use case and the message that I want to convey, it isn't going to change too much. So we're just going to stick with this one. To find the factors of the number 15, it's going to take approximately 256 possibilities. And that is a lot of possibilities to go through until finally, at some point during those 256 possibilities, the computer will be able to find the factors of 15, which in this case are 3 and 5. Right, and here's an example of Shor's algorithm. Now this is a massive number, like, what's even going on over here? Well, this is sort of a common number that's used in RSA encryption. And you can see how many numbers there are. I believe that's about 150 or maybe even 300. That's a very, very big number. And this is the sort of number that you'd expect to see in an RSA algorithm. Now, here are the factors of this number. Again, they're massive, right? So how do you actually compute this using a computer? Because if a computer were to go through all of the possibilities for this number, there'd be, well, these many possibilities. That's kind of crazy. So how are computers meant to do it? Well, it's pretty simple, actually. They can't. So classical computers can do this calculation in a reasonable amount of time. It's a problem. However, quantum computers, they can. So Shor's algorithm, what does that actually do? Well, imagine going through all of these possibilities on a classical computer, one after the other, and so on, until you finally reach the factors that give you the answer 15. So Shor's algorithm essentially gives you the possibility to search through all of these possibilities simultaneously with about 8 qubits or 8 quantum bits. And that is the fascinating thing about Shor's algorithm. It allows you to go through all of these possibilities with just 8 quantum bits or 8 qubits, compared to doing each of these processes individually with, let's say, a single bit or a couple of bits for each possibility and doing them iteratively, one by one. But with Shor's algorithm, you can execute all of them at once, all of the possibilities, you can test all of them, and you can do that using just 8 qubits, which is absolutely insane. So with these number of possibilities to go through, and that's a lot of possibilities, we really end up with, two options here. Either, if we do it classically, it'll basically take an infinite amount of time because that's a lot of possibilities to go through. Or if you would do it using a quantum computer, and let's assume, let's say 2000 qubits, it would take about 9.2 years. I mean, it's better than the previous one, so basically infinity, but it still takes 9.2 years with 2000 qubits. So that isn't, something that we can still feasibly do, right? So what about that? Well, scientists estimate that if you had about 20 million qubits, and that's a lot of qubits, mind you, that would take 9 hours to break an RSA encryption. So 9 hours with 20 million qubits, and if you have, let's say, 2000 qubits, which is a lot more realistic, it would take you about 9.2 years. So yes, it's better than infinity for sure, but practically, actually breaking an encryption scheme like this, it won't really retain any of its benefits after 9.2 years. Or there'd be a very, very low chance of it. And so a hacker's motive to do this would basically be gone by then. So what's the reality of quantum computing in this day and age? Are these things really possible? Do we have 2,000, 20,000, or 20 million qubits to actually use? Well, no. Unfortunately, we don't. In fact, we're actually very limited by the number of qubits that we have. So the reality is that IBM's biggest machine, just 433 qubits. We said that it would take 9.2 years for a 2000 qubit machine, but if you just have 433 qubits, that's pretty bad, And that's not the only thing. We have another issue to consider as well. These machines, they're not perfect. In fact, they're quite the opposite. They are error prone, meaning that they get a bunch of errors. Your computations are not perfect. So the reality of the situation is that your machines have errors. They won't compute as fast. If you use error mitigation or error correction techniques, they may not work as well, or it may extend the time of the computation by a lot, and many other similar problems as well. You need to keep them under dilution refrigerators at very cold temperatures, prevent any sort of environmental noise. It's a very difficult task to actually remove or prevent errors in a quantum computer. So the problems are pretty obvious. The first is scalability due to noise, right? We have noise from our environment, and that affects our ability to scale the qubits because our results would be skewed. They'd not be as accurate as you want them to. But if we have error correction, that isn't a problem. The problem is that we don't. So we do not have very good error correction, error mitigation, or any of these similar techniques to actually reduce or negate these errors completely. We do not have these techniques made right now. And that is why quantum computers, practically on the hardware side, are so limited in today's day and age. And this is, well, it's definitely very comforting to us, as users of the internet and technology in general. But there's still another problem which we have to consider called SNDL, or store now, decrypt later. So what this basically is, and you might be able to guess by the name, is hackers take encrypted data and just simply store it. You can still get encrypted data pretty easily by doing packet sniffing or basically sensing a network for transactions going on and just storing that encrypted data. Even though you can't use it, at least you can store it, right? So what hackers are planning on doing is storing a bunch of data, credit card data, transactional data, RSA data, all of these different kinds of data. They plan to store them and then decrypt it later when quantum computers actually come onto the scene. And when they have that many qubits, when they have that level of error correction, that is what hackers are planning on doing, which is obviously very dangerous. So, post-quantum encryption algorithms, these guys are here to the rescue. What are they? Well, NIST, the National Institute for Standards and Technology, they've essentially partnered with researchers all around the globe and held a competition to find the most efficient post-quantum encryption algorithms. These are classical encryption algorithms that are resistant to quantum attacks. And they came up with quite a few. So what are they? Well, the first one is Crystals. Crystals does key encapsulation as well as digital signatures. And this is pretty much one of the most popular ones, at least in my opinion, out of the three that we're going to see over here. It is very robust. It has multiple implementations or variations that have been implemented. And to be honest, it is my personal favorite. So the first one is Crystals. Second is Falcon. This is specifically for compact digital signatures. This increases, the speed it takes to actually implement these digital signatures, the time it takes to encrypt and decrypt, and so on. And it makes the whole sort of sending process to actually send the information or the digital signatures or the data from one place to the other. Since the signatures are a lot more compact, it won't take as much storage space, and hence the sending and receiving of data is much quicker. The final algorithm is Sphinx. This is a hash-based digital signature algorithm, pretty similar to the other two as well, although it does have its unique kinks as well. So that is the end of my talk. It's a pretty short one, but I hope you got a good general overview of what quantum cybersecurity is, what Shor's algorithm is, and what all of this holds for us in the future. I just want to talk a bit about QUAE. So QUAE is an organization that I'm leading alongside a few other people here in the UAE. And our mission is to democratize and advance quantum computing education, empower individuals from diverse backgrounds to explore, understand, and harness the power of quantum technologies. We are under a bigger organization called QWorld, which does these same global initiatives. And you could say broadly what our vision is is to create a world where quantum computing is accessible, understood, and harnessed by a broad and diverse community. We envision a future where quantum technologies revolutionize industries, solve complex problems, and unlock unprecedented possibilities. Whether bad or good. I mean, it's sort of a mix between the both, as you could clearly see from this presentation. So, our initiatives, what have we done so far? Well, Coders HQ, it's a government entity in the UAE that we've partnered with on multiple occasions, including this one, where we did a quantum computing hackathon at Zayed University. We also did a demo of New York University Abu Dhabi's SpinQ quantum computer. This is a 2-qubit nuclear magnetic resonance, or NMR, quantum computer, and we did a demo for this for our community live on Zoom. And then finally, we have regular meetups. This was our first one on the 31st of May, quite recent actually, at Coders HQ. And we talked about quantum computing, what it holds for the future, and also taught sort of a bit of Qiskit basics. Qiskit, it's a library which you can use to program quantum computers. And we covered a lot of basic quantum computing concepts. It was quite a fun experience in general. And so I invite all of you guys to join us for our initiatives, join us on our Discord servers for education-related courses, workshops that we regularly organize. We have unpaid internships, opportunities to work with amazing researchers around the globe, and also opportunities for independent funding and doing your own research and sort of advancing the field of quantum science. So I invite you guys to join our socials. And thank you so much for attending this talk. I hope you enjoy the rest of the conference.